In the last lecture, we considered the motion of an object in a plane and studied the motion of a projectile. In this lecture, we continue with the motion in a plane and take another example of this motion in a plane. And this time, we are going to study circular motion, motion of an object in a circle. Here, you have got an object moving in a circle, and if the velocity is v, and we take the velocity to be constant. If the velocity is v, then the time period is 2 pi r by v, where r is the radius, and the frequency nu is 1 by t, which is v by 2 r, or we can write v as 2 pi r times nu, where nu is the frequency. Now, why is it so important? You see, in a circle, a point, the object is moving with velocity v in this direction, tangential to the circle. When the object is here, it is moving tangential again to the circle, but here it tends to go off the circle, here also it tends to go off the circle along the tangent. That means, there is a force which is bringing the object back to the circle, so that it keeps moving in a circle. I have shown this by these arrows. The force is along these lines. It went off the circle, but it was pulled back, and the result is that at all points it is moving with the constant velocity v on the circle of radius r. As I showed you in the last slide, this means that there is a force acting on an object which is moving in a circle, which is all the time pulling it towards the center of the circle. This force is called the centripetal force. The direction of the force keeping the body on a circular path is along the radius, because it has to pull the body towards the center, therefore, it is along the radius. But what is its magnitude? How strong is this force? To find that, let us start with this construction. We take the body to be at p, and it is moving with velocity v along the tangent. After a very short time delta t, it moves to q, but its motion is again along the tangent with velocity v, and the angle covered in this is angle theta. So, the velocity here is v at p, the velocity at q is also v, I have drawn parallel lines if you notice, and the change in velocity is delta v from the final position minus the initial position, that is the change in velocity, that is delta v. So, velocity is v here, but in the interval there is a change in velocity. You know, let me remind you that what acceleration is. Acceleration is a change with time in the magnitude or of velocity, a change with time in the direction of velocity, which we have in this case. We have the velocity in this direction, then in that direction, and the change in velocity is delta v, and therefore, delta v is acceleration. How do you find this acceleration, the magnitude of this acceleration? The magnitude of the acceleration is obviously the change in velocity delta v divided by the time taken, that is delta t. So, we shall find delta v by delta t. How do you find that? We compare this triangle OPQ with this triangle formed by velocity v and change in velocity delta v. These two triangles are similar. Just to show you that they are really similar, I have rotated this triangle, so that I have made it in the same direction as this triangle. So, you can see now that these two triangles are really similar. If they are similar, then r by v must be equal to v delta t, this is v delta t, this is delta v. So, the v delta t by delta v must be equal to r by v. R by v must be equal to delta v by q p, which is v delta t. So, this is the formula for similar triangles, and from this we can easily find delta v by delta t. The magnitude you can see easily, in fact, is v squared by r. Delta v by delta t from this equation is v squared by r. This is called the centripetal acceleration, v squared by r. In terms of the angular frequency, it can be written as omega squared r, where omega is the angular frequency of rotation. This is an important relation, and I hope you have understood how this formula is derived. If there is acceleration, there must be a force, and this acceleration, the centripetal acceleration, is along the direction to the center of the circle, and therefore, the force is also along the line joining this object with the center of the circle. And if m is the mass of the object, then the centripetal force is m v squared by r. M into v squared by r, v squared by r you remember is the centripetal acceleration, and in terms of angular frequency it is m omega squared r, and in terms of the frequency it is equal to 4 pi squared m nu squared times r, where nu is the frequency of the circular orbit. You see, I have shown you here that this force shown by red arrow is the centripetal force. It must be noted that this force comes into play as soon as a body enters a curved path. It is not necessary that body goes through a complete circle. No, as soon as it enters a curved path, the centripetal force comes into play. This is very important to remember. Students forget that it need not make a complete path, complete circular path. Why is centripetal force so important? Let us take one simple example. If the earth were stationary, what would happen? The sun would attract it and the earth would fall into the sun. Sun has such a strong gravitational field. However, if the earth is moving in a circular orbit, then it requires centripetal force, and this centripetal force is provided by the gravitational force between the sun and the earth. So, this gravitational force is used as the centripetal force for the motion of the earth around the sun, and therefore, the earth does not fall into the sun. In a way, you can say that the centripetal force offsets the force of gravitation. Now, existence of centripetal force has very important implications for the motion of vehicles on curved roads. You see, you do not have all the time roads which are straight, most of the roads are curved, and therefore, if we are moving in a curve, we need centripetal force. And who provides centripetal force? Let us see. You are familiar with this friction, so I will just skip this. You know, friction is a force which is in the direction opposite to the intended motion of the object. It is our experience that when force is applied on the body, it does not move initially. As we increase the applied force, the force of friction also increases in the same proportion as the applied force, and the body does not move. A stage reaches, however, when frictional force is no longer able to withstand the applied force and the body just starts to move. I show you this in a graph here. You see that the force of friction was increasing all the time, and at this point the force of friction was not, beyond this point the force of friction was not sufficient to prevent the motion of the body, and therefore, this is called the force of static friction. The maximum force required just before the body moves is called the static friction, and it is given by the coefficient mu s times n, where n is the normal reaction of the surface on which the body moves. For a static body in equilibrium on a surface, let us write the equation of equilibrium. F static maximum is mu s times n is mg, therefore, F static is nothing but mu s times mg. And remember that this F static is the maximum force. Normally, the force of friction is smaller than this, therefore, F static is always less than or equal to mu s times n. Let me remind you of your experience. If you are on a curved road driving a bike, you have to bend a little towards the inner edge of the road. Same thing happens when you are in a car or when you are on a bicycle even. You have to bend slightly towards the inner edge. Why do you have to do that? To supply the necessary centripetal force, so that you can keep moving in a circular path. So, to maintain a car moving on a curved road, the car needs to be supplied with the necessary centripetal force. In the absence of this force, the car tends to skid towards the outer edge. If you do not bend, remember, then you tend to fall towards the outer edge. This results in a frictional force acting towards the center of the path. Since you are being pushed towards the outer edge, there is a force of friction towards the inner edge. This frictional force must supply the necessary centripetal force. And what is this frictional force? We have been seeing this. This frictional force is mu s times mg. And what is the force that it has to supply? mv squared by r. So, we equate the two and we get V equal to mu s times r g, the root of that. It is maximum because mu s is the maximum coefficient of friction, because mu s times mg is the maximum force of friction. Therefore, this is V max. If the velocity of the car exceeds this, the friction will be unable to provide the necessary centripetal force and you can meet an accident. Now, while traveling on a curved road, you must have experienced that you have to bend towards the inner edge of the road, as I have explained. To facilitate this, the outer edge of the road is built slightly higher than the inner edge. That is, the road is shaped like this. This is called the banking of the roads. The road is not plane, but road is like this. There is an angle at which this elevation takes place. And here I have tried to show this is the outer edge of the road, this is the inner edge of the road, r is the radius of the curved road, and you have also tried to show you how the road is banked and the car is on that banked road. All right, but by what angle should I bank the road to provide the necessary centripetal force? Let us see. The amount of banking depends on three factors. One, the radius of the curved road, obviously because the force is mv squared by r. The second is the estimated typical speed of vehicles on that road, because mv squared by r. So, we need v. So, v is we take as the typical speed on that road. And third is the estimated friction between the tires and the road surface. What is the force of friction which the tires and the road surface provide for the motion of vehicles. Even planes, when they have to take a curved path, they have to bend, and I have shown you the bending here. The bending is to provide centripetal force, so that the plane can safely go round the circular orbit. Now, let us come back to the road. I have shown you here the road which is banked at an angle theta. I can't show the car, but here is an object, and let me show you the various things. This is the normal reaction of the surface on this object, and this is the component which is perpendicular or in the vertical direction, n cos theta. This is the weight of the object vertically downwards, and this is the component n sin theta. This is towards the center of the road, and it is this component which would supply the necessary centripetal force, this n sin theta. So, we write down the equations of equilibrium. N sin theta is to provide mv squared by r, n cos theta is to balance the weight of the object, and therefore, we divide one by the other, we get tan theta, which is equal to v squared by r g, or v is equal to r g tan theta. This theta is the banking angle, and as you can see, it depends upon the radius, the acceleration due to gravity, and so on, and the velocity of the object. This is the safe velocity. If we are within this velocity, you won't meet an accident. Otherwise, if the velocity exceeds this, you can have an accident. Now, if V0 is r g tan theta, root of that, then the friction between the tires and the road is not required to provide the necessary centripetal force, because we have not considered frictional force. Therefore, without friction, the banking at an angle theta can provide velocity V0 for the vehicles on that curved path, and if they drive at velocity V0, then friction is not needed. That means, tires are not, they will not wear out, and they will last much longer if you drive at this velocity. The friction between the tires and the road is not required to provide the necessary centripetal force. So, there will be little wear and tear of the tires. Your tires will have a long life if you drive at this speed. Now, let us take the case that there is a friction between the tires of the vehicle and the road. You can see that we have drawn this, the normal reaction n cos theta, n sin theta, and also the weight, as we did earlier, and we add to it now the frictional force, and The frictional force will have components F cos theta and F sin theta, and we collect all the components now in the vertical direction and the horizontal direction and write down the equations of equilibrium. We have got vertical n cos theta, mg and f sin theta. Along the horizontal we have got f cos theta, n sin theta and mv squared by r. So, we will write down the equations of equilibrium. N sin theta, when friction was absent, we had n sin theta equal to mv squared by r, but now friction is present. So, we have mu s n cos theta, n cos theta plus mu n sin theta equal to mg. So, these are the two equations. We can solve them for v squared and we get v squared equal to g r times mu s plus tan theta divided by 1 minus mu s tan theta. This is the velocity with which the vehicle can move on the road, which is banked at an angle theta, and the tires of which provide friction coefficient mu s on that road. Let us check this expression. If there is no mu s, then we should recover this formula v squared is equal to g r tan theta, and we do that. So, therefore, we are on the correct road. So, if mu s is 0, we get back the expression we derived earlier. This serves as a check on the correctness of the above expression. Also, since mu s is the coefficient for the maximum static friction, I remind you again, this value of v is the maximum value of velocity on that road, which is banked at an angle theta and whose surface and the tires of the vehicle provide coefficient of friction mu s. It is not safe to drive on a curved road at a velocity higher than v max, because the friction is not able to supply the necessary centripetal force. As a result, the car is likely to skid towards the outer edge of the road and accident can occur. So, let me sum up. In this lecture, we have seen how important the knowledge of circular motion is. It tells us how fast we can move on a curved road without hurting ourselves. It also tells us how important the friction between the tires of the vehicle and the road surface is. You must have seen the advertisements of various tires made by various companies, and they always emphasize the grooves on the tires. These grooves provide the frictional force which is necessary, as we have been seeing. In the next lecture, we take up some problems associated with the motion of objects on circular paths. There are many other problems which we shall consider in the next lecture.